So suppose, when you use a retarder plate, you create different states of polarization. But with a retarder plate, you can also analyze the state of a particular polarization in a light that has been given to you. Let us see. So we will discuss 5 cases. What are the 5 cases? Plane polarized light, elliptically polarized light, circularly polarized light, partially polarized light, and unpolarized light, meaning it contains all states of polarization, which is totally randomly polarized, right? So all states of polarization are mixed. The partially polarized light is that you have one polarized beam and then some normal light mixed up with that. Okay, so let us now look at all of them. You will use Malus law. What is that? That suppose you have a particular plane of polarization. Yesterday we discussed this thing. You have a particular plane of polarization. Now you make this light with this particular orientation of polarization pass through an analyzer. The analyzer is usually a crystal. A crystal is made up of atomic planes. The little gap in the planes will allow the polarized light to pass through. If the gap is perfectly aligned with the plane of polarization, then all of the light will filter through. But if the gap is slowly rotated away from the plane of polarization, then a component of that will filter through. It's the cosine of the electromagnetic wave vector, and if it is at 90 degrees, then nothing will go through. Like it's like taking a narrow stick and making it pass through a narrow slit. If the stick is aligned with the slit, it will comfortably go through. But if you make the stick oriented 90 degrees to the narrow slit, then nothing of it will go through. So it is like this thing. So we will use this Malus law over here. So first case is plane polarized light. So plane polarized light means light is rotating on a plane. So here it is. The polarizer is simply a calcite or some birefringent or some crystal material, twice zero intensity in one full cycle of rotation of the polarizer. So that is very much understandable. You start with a perfect state of alignment. So let us say that this is the plane polarizer alignment. Your analyzer material has got its crystal lattice orientation such that all of it this electric field orientation is passing through, oriented electric field is passing through the gap. And then you slowly rotate the analyzer. So when the analyzer the field this atomic plane spacing is at 90 degrees, nothing will go through. And then in a full cycle there will come another stage when there will be another 90-degree orientation between the two. And so in both cases you'll get zero intensity in one full cycle. Okay, so that's plane polarized. Now you have been supplied elliptically polarized light. So something like that, going around like this thing, right? Elliptically polarized light. How will you then detect elliptically, make sense of elliptically polarized light? A simple way is to make the elliptically polarized light pass through a quarter wave plate. If it is passing through a quarter wave plate, note that elliptically polarized light has already a phase difference of pi by 2 built in it, right? So when you make an elliptically polarized light pass through a quarter wave plate, it will introduce another pi by 2 phase difference. So 2 pi by 2 added to, pi by 2 plus pi by 2, it will immediately become pick up a phase difference of pi. So once it has picked up a phase difference of pi, then it has become a linearly polarized light, and it will show the same behavior as in the previous case. So if you have to try all these things. Some you have been given the information that light has got certain state of polarization. What will you do? You just make it pass through this analyzer, a quarter wave plate, and see what condition is satisfied. So twice zero intensity in so a quarter wave plate, QWP. When the light is made, this elliptically polarized light coming from the left is passing through the quarter wave plate, it will be converted to a linearly polarized light, and then after that it will be made to pass through the analyzer, and this analyzer will analyzer is also polarizer in a sense. So total zero intensity in one full rotation of the polarizer or analyzer. Suppose you did not have a introduce this quarter wave plate, right? Then what would have happened? What would have happened is that you rotate the analyzer. When the alignment is along the major axis of this ellipse, large amount of light will go through. And then when the alignment of the analyzer is along the vertical axis of this ellipse, much smaller amount will go through. So what will happen is that without this quarter wave plate, the intensity will vary between a maximum value, which will correspond to the major axis, and a minimum value, which will correspond to the minor axis. So that is the case of elliptical polarization. Let's look at the third case. It's the same thing. Circular polarization and elliptical polarization, there will be only one difference, that the intensity will be the same all over this cycle. Quarter wave plate, linear polarization will be created. You make it then pass through the polarizer analyzer, and it will be rotate this thing. Light will go through, and twice there will be zero intensity in a full cycle. And if you did not introduce this quarter wave plate, then throughout it will show an intensity that is constant. That is not surprising, because everywhere the amplitude of the electric field is the same, and the intensity will be the square of the amplitude, and so the intensity measured will be the same. Here, on the other hand, there will be a higher intensity because the amplitude is longer here compared to here, right? So there will be a greater intensity and there will be a lesser intensity over here. And so there will be a maximum intensity and a minimum intensity, but neither, I mean, it will not be zero. So some low non-zero value of the intensity. What about partially polarized light? Partially polarized light is a mixture of linearly polarized light and unpolarized light, right? So what will happen is that if you make this thing pass through a quarter wave plate, the intensity will vary. Once again, quarter wave plate will linearly polarized light will convert it to an elliptical polarization, and also the unpolarized light will also be converted to a state of elliptical polarization, because all of them will, the random orientation will now be oriented. So basically all of them will pick up a phased angle of, both will pick up a phase a difference of pi by 2, and so it will correspond to the previous case that we discussed. In case 2, intensity will vary between a maximum and a minimum value with or without a quarter wave plate. So that you will get. Okay. So yeah, and then the last case is randomly polarized light, because there's all states of polarization, so the intensity will remain constant with or without a quarter wave plate, so you will capture everything. So basically polarization means that along certain directions you will have greater intensity, much greater intensity, if you have a perfectly linear polarization, and if you have elliptical polarization, you will have greater intensity in a certain direction as compared to the other direction. Anyway, so that was just how you analyze it. Now we shall come to an interesting topic known as optical activity. Optical activity is, let's now try to see what is this. Uh, this is of great importance in nature, actually. Some of you are interested in quantum information and all of that. So, in due course of time, biomolecules and all of these things. I mean, I think there's this idea of something called DNA computing or something. A colleague of mine used to do that. Professor Rajendra also knows him, so he used to work in this area. So biomolecules will become storage devices of repositories of information. So optical activity is actually quite closely related to biological systems. We shall discuss some basic idea of that. So let us now see. So the plane of vibration of a linearly, first let us try to understand what it is. Plane of vibration of a beam of linearly polarized light undergoes a continuous rotation as it propagates along the optic axis of a quartz plate. So this is a very strange kind of a behavior. You have a material, let's say a column of material, transparent material, and light is of a certain polarized state is made to pass through that material. Suppose you had water, right? Then nothing would have changed. The plane of polarization or the plane of the vibration of the electric field would have just remained unaffected and passed through the water and emerged from the other side. Water column and emerged from the other side, right? But something quite different happens in an optically active material. What happens is that the plane of vibration starts rotating as the light travels through this material, this optically active substance, and emerges from the other end with a completely different orientation. So it's just like a cycle that goes on. So I just let me just take you, let's say that you have this thing, you have a circular orientation, right? So this orientation is happening even as the light is propagating. And so you start with a this sort, maybe I should represent it with this diagram. So here you have a linear state of polarization. This state of polarization is fixed, right? You make this thing pass through water, z axis is pointing towards you. You are, let's say it's passing through a water tube. So it enters the tube at one end, emerges from the tube at the other end, and all along this plane remains fixed. But if instead of water, you have an optically active substance, a very simple optically active substance is normal sugar solution. So if this plane of polarization is, I mean, if this light is made to pass through that tube containing sugar solution, then this plane of polarization will start rotating even as the light will propagate, and then it will emerge at some with some other orientation at the other end of the tube. At what angle of orientation it will emerge will entirely depend on the length of the tube or length of the water column through which the light has been made to travel. So let's now look at this thing. So it undergoes a continuous rotation as it propagates, continuously rotating along the optic axis of a quartz plate. So this was discovered by Dominic Arago. In quartz, it is seen. Quartz is a very strange kind of material. As I showed you, it's birefringent material. It is optically active material. If you make light pass through optic axis, it is piezoelectric material, although we are not doing piezoelectricity over here. So quartz can be used for various contexts. I mean, to a material scientist, quartz is a very useful material. Anyway, now this rotation can be right-handed, we call it dextrorotatory, or left-handed, we call it levorotatory. Dextro means clockwise rotation. So you look at the light approaching towards you. If the rotation of the plane of polarization, linear plane of polarization, is just rotating now, if the rotation is in the clockwise direction, then it is dextrorotatory, meaning towards your right hand as you're sweeping your right hand downwards. So dextro. And levorotatory, left-handed, if it is in the anti-clockwise direction. Okay, so dextro clockwise, levo anti-clockwise. Now here it is. Quartz can show both kind of behavior, but the same quartz sample will not show both behavior, because here it is. First, let me read out the statement. Dextro or levorotatory behavior in quartz depends on the left-handed or the right-handed structure of the quartz crystal. So these are known as enantiomorphs. So meaning, so now we come to something, we are left to conclude something, that it is not just the molecular formula that is enough. You also need the way the molecules are stacked inside that material. So when you have in these enantiomorphs, you have left-handed and right-handed structure. The one will be the mirror image of the other. So left-handed quartz and right-handed quartz will show dextro behavior or levo behavior accordingly. I mean, one kind of right-handed behavior and left-handed behavior. So these enantiomorphs are mirror images of each other. But then molten quartz is not optically active material. So basically, then it means that the crystal structure is important, not just the molecular formula, because the molecular formula remains the same, but it's the arrangement of the molecules that will matter. So optical activity will depend on the crystal structure. The crystal structure will imply the arrangement of the molecules. And there you have. Uh, there are other cases also. Here it is: optical activity seen in liquid and vaporous turpentine. Sugar solution, sugar shows optical activity in a solution. Yes. And in the cases where you have optical activity shown by liquid material, then clearly the optical activity in a liquid, there is no arrangement of crystalline structure. So it is not so much about their arrangement as it is about the property of the molecule. So you can see there's a vast range of interesting phenomena over here. So some things are optically active, not in the liquid phase, but in the solid phase, in which case it is not so much the molecular structure that matters as the arrangement of the molecules in the crystalline structure that is important, right? But in some other cases, the optical activity is shown in a solution state or and a molten state. So it is the optical, I mean, it's the molecular behavior that is key over here. And then there is even more strange behavior. There is this material rubidium tartrate that is levorotatory, left-handed rotation in the crystalline state. But in a so crystalline state, it's solid. But you dissolve it, like salt is crystal, but you dissolve the salt in water, it becomes a solution. So this rubidium tartrate will show levorotatory behavior in the crystalline state, which means that it depends on the structure, but it will show dextrorotatory behavior in a solution. So these are the optical activity behavior. I'd just like to touch on some biological behavior, biological implications. For instance, sugar always shows right-handed behavior. That's why we have this dextrose, the name dextrose. But so there is no left-handed sugar. Incidentally, left-handed sugar is, I mean, you can manufacture in lab or whatever. The left-handed sugar will be highly poisonous, quite poisonous for upon being consumed. So you can immediately see that the right-handed sugar can be absorbed by the body, the enzymes and everything, but the molecular structure of left-handed sugar will not be absorbed and it will become quite toxic for you, right? On the other hand, amino acids, the structure of proteins, the basic material of proteins, amino acids show left-handed behavior. They don't show right-handed behavior. So in the evolutionary track, somewhere along the way, there was a preference for left-handed amino acids only, somehow, for whatever reason. At least I do not know. And so evolution has designed us in such a way that we all have left-handed amino acids and not right-handed amino acids. Although it could have been very easily possible that it might have been right-handed. So because molecular reaction wise, there shouldn't be any difference. Okay, so Fresnel gave a very elegant phenomenological explanation for optical activity. It's a very simple mathematical discussion and phenomenology. Of course, it doesn't, as you can see, there is such a vast range of properties and features in optical activity. Fresnel's theory doesn't at all give any answer to any of these things. Anyway, most of these features require pretty sophisticated chemistry to find out. So Fresnel did not have any idea of all that as well. But nevertheless, the theory that he gave is quite elegant. So let us now look at it. So linearly polarized light is a superposition of two states of circular polarization. This is completely the opposite. That is how you start this discussion. You remember our discussion held some time ago, just a little while ago, today only, that circularly polarized light or elliptically polarized light, we say, is the outcome of the superposition of two linearly polarized states, right? With a phase angle difference of pi by 2. But here, Fresnel is starting by saying that linearly polarized light is the other way around. In the previous case, we said circular polarization is the outcome of the superposition of two linear polarizations with a phase difference of pi by 2. But here it is the opposite case. You have got two states of circular polarization, and when you superpose them, you get linearly polarized light. Let us see how. So here you have case over here. Ex is equal to E naught cos kz minus omega t x cap. Ey is equal to E naught cos kz minus omega t plus epsilon y cap, right? And the propagation of these two waves is happening along the z axis, and together they sum up and create a certain state of polarization. If epsilon is an integral multiple of pi, you will get linear polarization. If epsilon is pi by 2, half integral of pi, then you'll get circular polarization or elliptical polarization. Well, in this case, circular polarization, because the amplitudes are equal to each other. Let us add these two vectors. Vector E, the total superposition will be vector Ex plus vector Ey. So E naught will be equal to cos kz minus omega t x cap and cos kz minus omega t plus epsilon y cap. Okay. So we have discussed this thing, as I said, when epsilon is equal to minus pi by 2, you will have right circular polarization. So this is what you have. And what we do now is we put a state of, uh, remember, Fresnel is starting with two states of polarization, two states of circular polarization. So we'll have to create those states first, right? So when do we have a state of right circular polarization coming out of these two sums, the sum of these two vectors? The right circular polarization will come out when epsilon is equal to minus pi by 2. We have discussed that already. So when epsilon is equal to minus pi by 2, you have cos kz minus omega t minus pi by 2. And so we extract the minus sign over here. And so cosine will kill the minus sign. It will be pi by 2 minus kz minus omega t. And so it will be sine kz minus omega t. So sine kz will substitute this term over here. And so this is the state of right circular polarized light, right? The right circular polarized light is emphasized by the subscript R. ER is the right circular polarized light. Its equation is this: cos kz minus omega t along the x-axis, sine kz minus omega t along the y-axis. And when epsilon is equal to pi by 2, it is left circular polarization. Okay. If it is left circular polarization, then we shall have to tailor our equation accordingly. So cos pi by 2 minus omega t minus kz, and so this thing will become sine omega t minus kz, because cos 90 degree minus this thing will be sine of that. And then this thing, I take out the minus sign, it will be minus sine kz minus omega t. And so this will be the state of left circular polarization. This is the along the x-axis, and this is minus sine kz along the y-axis, L as in left. So let us now add these two states. So Fresnel starts his theory of optical activity, mathematical theory of optical activity, by saying that linearly polarized light is a superposition of two states of circular polarization. Circular polarization, hence the amplitudes are constant. And so this is along the x-axis. It is the same for both. And for the y-axis, we tune the value of epsilon, and we get these two states. This is the states plus sine kz minus omega t for right circular light, and minus sine kz minus omega t for left circular light. Now, linear polarization will be the superposition of these two states. So ER plus EL. When you add the two things up, this minus term and the plus term over here will cancel out each other, and you will just have 2 E naught cos kz minus omega t x cap. Of course, we are talking about things in vacuum. Let us now try to understand this thing. So linearly polarized light is a superposition of these two circularly polarized states. Okay. Now, so this equation we have framed for vacuum, but in a polarizing material, in an optically active material, this equation will have to be altered. Let us see how. So in an optically active substance, the left and right circular polarized rays will propagate along the z-axis with different velocities. Basically, what have you got now? Earlier, you had birefringence. If you can please recall, I'll just take you back to something. Here we have got, while we discuss this very basic thing, we had here Birefringence refers to separation of the E ray and the O ray into two linear states. This is a linear state on the plane for the E ray, and this is the uh, linear state of polarization for the O ray away from the perpendicular normal to the plane, right? So these are two separated states, and when you superpose them, you get the full light, one with linear polarization on the plane and the other with linear polarization normal to the plane. But now what you have, and then you introduce, by the way, you introduce a phase difference of pi by 2, and the superposition state will be a state of circular or elliptical polarization depending on the values of the amplitude of the two vectors. Now, but here you have the other way around. Things are propagating, the left polarized light and the right polarized light. Remember, this thing, right circular polarization, this is actually a rotating electric field, a rotating electric field vector. It is rotating in the right direction, right circularly polarized direction, and this thing is left circularly polarized. Why am I calling this thing right circularly polarized direction? Because it's minus pi by 2. Minus pi by 2 means negative angle. Zero angle is the horizontal line on a circular scale, and negative angle is going clockwise, downwards along the right hand direction. So that's why this is right circularly polarized light, and this will be in the positive angle direction, plus 90-degree, going in the anti-clockwise direction, leftwards. So that is how the definition will come. So this light is rotating in the clockwise direction, and this light, the electric field of this light is rotating in the anti-clockwise direction. Now when they enter an optically active material, they will, the left and the right circularly polarized rays will propagate along the z axis with different velocities. Now you have got circular birefringence. When we talked about E rays and O rays in a calcite material, there was linear birefringence. Birefringence is double refraction. Double refraction will happen when there is a difference of velocity, like just at the start of the discussion, I mentioned this thing, reading out with reference to the first question that was given to me, that it is found that, I'm just reading from that section again, Jenkins White. It is found that for any direction of the wave front, there are two velocities for vibration of the vector d in two mutually perpendicular directions. And this is the fundamental aspect of double refraction. So you need to have differentiation of velocity for birefringence. In the previous case, it was linear states of polarization with two different velocities, therefore linear birefringence. And now you have got circular states of polarization, and so accordingly you have got circular birefringence. So now let us see what we have. ER is this, right? KR is the wave number for the right polarized light, and EL is for the left polarized light. KL is the wave number for the left polarized light. Now let us discuss why we are having separated wave numbers. Because you see, whenever light enters any material, transparent material, dielectric material, its velocity will change depending on the refractive index of that material. So if the velocity changes, now velocity, phase velocity of light is the product of the wavelength and the frequency. The question is, what changes? Does the frequency change? Does the wavelength change, or both change? It so happens that the frequency doesn't change, it is the wavelength that changes. And so if the wavelength changes, then the wave number k, which is 2 pi by the wavelength, 2 pi by lambda, that will also change. So in these two formulae, I have not changed the frequency. The frequency omega, omega is actually the angular frequency, 2 pi nu, that remains fixed. It is the wave number that has changed, and the wave number will bring about a difference in the wavelength, and correspondingly a difference in the phase velocity of the two lights. Let us see how we so here it is, we have this thing, omega is equal to 2 pi nu. This thing remains fixed, but k will change. K will be equal to 2 pi by lambda. And you note that these two equations are in the general form of the solution of a wave equation. F1z, this is the general form of the solution of a traveling wave. So z minus vt will be along the positive direction of the z-axis, and z plus vt will be the branch of the wave that will go along the negative direction. Here in this case, of course, both of them are propagating along the positive direction of the z-axis, therefore you have the minus sign. So this is the general solution of the wave equation. So if you have solved a wave equation, I mean, in mathematical physics or all of these things, this is a standard thing. Anyway, so let us now look at the argument of the wave equation, right? Look at this thing. The argument should be in this form: z minus vt, right? So let's not worry about the z plus vt part. So we have got kr z minus v omega t, and we have got kl z into z minus omega t. So we are writing this kr z minus omega t as kr has a common factor z minus omega by kr into t, and kl z minus omega t is kl into z minus omega by kl into t. Okay. Now, what is phase velocity? Phase velocity is omega, which is the angular frequency, divided by the wave number k. So now you can immediately see that this will be the velocity, omega by k, as per this formula. By just tallying with this formula is the phase velocity of the wave. You can just check for yourselves. Omega by k will actually turn out to be wavelength into the frequency. 2 pi nu divided by 2 pi by lambda. 2 pi and 2 pi will cancel, and you'll get omega lambda into nu. So Vr will be omega by kr. And so what about the refractive index? The refractive index will be c by the speed, and so it will be c by into kr by omega. And so kr will be equal to refractive index times omega by c. Okay. And similarly, VL will be omega by KL, and the corresponding wave number will be NL omega by C, just following the previous track. And NL will be equal to C by VL, C KL by V. And so KR will be equal to NR into omega by C. KL will be equal to NL omega by C. What about omega by c itself? Omega doesn't change, 2 pi by nu. And what is c? C is the speed of light in vacuum, and the speed of light in vacuum will be the frequency of light, which doesn't change, times the wavelength of light in vacuum. So omega by c will be the value of 2 pi by lambda naught into 2 pi by lambda naught, and that is k naught. So basically kr is equal to nr into k naught, which is the wave number in vacuum, and kl is nl into k naught, where k naught has been defined as 2 pi by lambda naught. Okay, so this is what we shall now do. Our formula is this: E is right circular state plus left circular state, the vectors. So E naught is equal to kr z minus omega t sine kr z minus omega t, etc., x cap, y cap. And this is for the left circular state. This first part is the right state, and the second part is the left state. When you add the two of them up, let us see what we get here. You have got two x components, you have got two y components. We gather the x components and we gather the y components. And then we apply these two formulae. The trigonometric identity: cos A plus cos B, sine A minus sine B. Cos A plus cos B and sine A minus sine B. Okay. So the identity is 2 cos A plus B by 2, cos A minus B by 2, etc. And for this thing, the sine part is 2 cos A plus B by 2, sine A minus B. A is equal to KRZ minus omega t, B is equal to KLZ minus omega t. This will lead to something pretty interesting now. A plus B, you will have KR plus KL into Z by 2, these things added up, right? A plus B by 2, and you have minus omega t by 2. The 2 will cancel, and you'll have minus omega t. What about A minus B? A minus B will cancel omega t's, and A minus B by 2 will give you KR minus KL by 2 into Z. Okay, so the the field that we shall get now will just be this. Adding these two things up, right? What we will get is E will be equal to 2 cos, let's see, this part, x here. This is 2 cos of a plus b by 2. So these two things will give you 2 cos of a plus b by 2, 2 cos of a plus b by 2, and then cos of a minus b by 2, and this. So when you put these things together, you will get 2 into E naught into this is the cosine part that you will get, cos of kr plus kl by 2 z minus omega t, and then notice what will happen to uh, the amplitude part. This part, sine a minus sine b, will be sine of a minus b by 2 and cos of a minus b by 2. This part that you have. Let us now look at this part a little carefully. This part inside the curly brackets does not contain any time. Basically, this is now an amplitude part, whereas this part in the square bracket contains space and time. This is the phase part. So the phase part is a scalar part, the amplitude part is a vector part, and it does not contain any time, but it contains these two things, and it contains z as a variable. Let us see now what you will have. Just consider this one thing. Suppose the material were not optically active. What will you get out of this material? Please just carefully note over here, if the material were not optically active, there would have been no difference between kr and kl. Kr would have been equal to kl. So the sine, so kr minus kl would have been 0. Sine of 0, this part would have vanished, and this part would have been 0. Cosine will give us just cos, this part will become 1, and you will just have 2 into a constant E naught into a constant orientation along the z axis, and then a phase part. But since these two things are not different from each other, as I've mentioned to you, this 2 E naught into this curly bracket part is the amplitude, and this part is the phase part in the discussion. We look at the amplitude part now. Okay, so we are writing this angle kr minus kl by 2 into z as alpha, and kr minus kl is nr into k naught kl minus nl into k naught by 2 into z. So this is alpha. Alpha is equal to nr minus nl, and k naught is 2 pi by lambda naught. The 2 and the 2 will cancel, and you'll have pi z by lambda naught. So basically, just please notice one thing. This is the amplitude part, and in the amplitude part, this alpha is a variable because z is a variable. Z is the length of the optically active material through which this light ray, linearly polarized light ray, is passing. So if that is so, with increasing z, what will happen? Let us look at this thing. If nr is greater than nl, then kr will be greater than kl, of course. If nr is greater than nl, then alpha will be positive for values of z greater than 0. So you start at z equal to 0. Your liquid or optically active material has got a length of z. As it is passing through z, alpha is changing its value. Alpha will have this value because this is non-zero. nr is not equal to nl. Alpha is a positive thing, and you will have this sort of an angular increase going up in the anti-clockwise direction, right? Alpha will be positive, you'll have anti-clockwise rotation. What if nr is less than nl? Then kr will be less than kl, and alpha will be negative. You will have a clockwise, alpha negative, meaning it will come down in this direction. You'll have a clockwise rotation. So you have a wave whose phase part, well, it's the usual phase part, but the amplitude part is rotating for increasing value of z because of the difference between kr and kl. That is the conclusion that you can draw from here. But Fresnel did something slightly different. Today I will end at this last point. Fresnel did something slightly different. His definition was that uh, this, you notice that alpha is negative for clockwise and alpha is positive for anti-clockwise rotation. In Fresnel's own theory, he said that the angle should be positive for clockwise rotation and negative for anti-clockwise rotation. So you have to choose the angle to be minus alpha and define a new angle beta. Beta is positive for clockwise rotation. So beta is equal to minus alpha. The definition of alpha is given over here, nr minus nl, etc. And so you put the minus sign, nl minus nr. So whenever you have a positive clockwise rotation, you have dextrorotatory material. Whenever you have a negative anti-clockwise rotation, according to Fresnel, this convention, you have levorotatory material. And so if the medium has a thickness of d, let's say z is d, then the angle through which the polarization vector would have rotated, the full angle is this, beta is equal to this. This whole treatment of Fresnel is taken from Eugene Hecht's book. I will just tell you what is the section in chapter 8, section 8.10. Chapter 8, section 8.10. You may please note this mathematical theory and this long discussion on optical activity. It is quite an interesting discussion. So, optically active substance. So, this is where we can logically end today's topic, optical activity. Tomorrow, we have one more session left. There, I shall finish off some final discussion on polarization, and I shall also try to connect all of these discussions with quantum computing. However, I have to inform you that I am no expert on quantum computing at all. Nevertheless, I shall try. So, Professor Rajinder, is that all right that we should stop the discussion over here and take any questions if there should be any? Hello? Hello? Are you hearing me?
Yeah, we can hear you.
So perhaps we should stop here today's technical discussion. And if there are questions, we can take some questions, because the next topic is specific rotation. It's a very simple topic, but logically we can apply a break here. Today's
Yeah,
topic.
sure. So
Yeah.
there are few questions here.
Yes.
I mean, this is related to quantum computing, though. So the
No.
participant is
At,
asking.
no. Please send me the questions so that even if I can't answer them right now, and probably I'll not be able to because I'm no expert, nevertheless I can prepare them for tomorrow.
Yes. So the question is: are these polarization states related to Bloch sphere rotations in quantum computing?
That I wouldn't be able to answer, but you can send me the questions this evening.
Webinar is being recorded.
Hello?
Yeah, just a second. So uh, basically, Bloch sphere is, I mean, they have this qubit where you have two states, zeros and ones. So
Okay.
probably, I mean, these states which you are discussing, these polarization states can be considered as these Bloch sphere states, which they are discussing. I'll send this question to you. Probably you can just check.
Yeah. But one thing offhand I can say that although we are discussing, see, yesterday at the very outset, I mentioned to all of you that light is a wave. And as such, it submits itself to three different phenomena: interference, diffraction, and polarization. But interference and diffraction can be shown by other kinds of waves also. But polarization is very specific to light with regard to its transverse nature. So, light is a wave. Polarization is a very much a wave phenomenon. However, we must not overlook the other fact that light, due to wave particle duality, is also a particle, right? And as such, all of these things could be seen as light, could also be seen as a quantum particle. This thing was done by Planck and Einstein, quantization of light, photon. So instead of saying a wave with two states of polarization, we can very easily also say a photon with two states of polarization. And as soon as you have a photon in two states, it's like a particle with some kind, just like, in the case of an electron, you have a plus sign and a minus sign, plus h cross, minus h cross, that sort of a thing. So in the case of a photon also, the two polarization states can become like two quantum states, and as such, then they can be the way you can make them repository of quantum information. Polarization states, they can be used to encode quantum information. So that is a basic principle. So that is not lost over here.
So probably
Yes.
you have already answered this question. We can move on to the next one, which is experimentally how we know that linearly polarized, the light is linearly polarized or circularly or elliptically polarized.
Just a while ago, I discussed, you see, if you take a linearly polarized light, right? And the analyzer discussion over here, I'm sorry, let me just go back to that page. So suppose you have been given some light and you have been told that this is in a polarized state. How will you know? So basically there are only two standard states of polarization, linearly polarized. So if you have a linearly polarized light, you make it pass through an analyzer. So this left arrow is linearly polarized light that is incident on the polarizer. The polarizer is also an analyzer. The polarizer can polarize and it can also analyze. So you make the polarizer, this rectangle, rotate by 360 degrees. If it is linearly polarized as in this diagram, the intensity will be extinguished twice, because on those two occasions, the grid of the crystals planes in the polarizer material will be perpendicular to this, and that will follow Malus law. Intensity will be cos squared theta, theta being the angle between the polarized state, and the grid spacing between the atoms. So that is how you test linearly polarized light. And if it is elliptically or circularly polarized light, then you simply introduce a quarter wave plate along the way. This is the elliptically polarized light. You introduce a quarter wave plate. Quarter wave plate, elliptical polarized light will have a pi by 2 phase difference built in it. So when you make it pass through a quarter wave plate, it will add another pi by 2. So both pi by 2s will give it a pi phase difference, and immediately it will become linearly polarized light, and then you can test it like this. So you just have to check all these things and then come to your conclusion. So this an analysis of polarized light, all these cases have been given, page 34 in the notes. Please just go through them. Hello?
Okay.
Yes?
Yeah. So next question is how is this possible that wavelength changes but frequency remains the same? Are they not reciprocal of each other? Is it something in relation to medium through which light is propagating?
No, that I can't really answer immediately. Yes, it's actually an interesting question. See, the velocity is changing. Phase velocity is wavelength into the frequency, right? So either wavelength can change, or frequency can change, or both can change. But it so happens that the wavelength changes, but the frequency doesn't change. Now, yes, I mean that's a fact, observed fact, but I can't offer an explanation. So probably, see, this is related to the material nature. So the frequency is perhaps linked to the frequency, the oscillations of the electric material, whatever it is. So, Professor Rajinder, may I please note this question for sending it to me, which I can think of and answer tomorrow. Right?
Okay.
Okay.
Probably it might be related to dispersion also. So let's say if you are having a single frequency, and if the electromagnetic field is experiencing dispersion, it automatically generates multiple frequencies within that particular field, even though the incident field might be having just one single frequency.
Okay, I'll check this thing. Now that you've given me this word dispersion, in Jenkins and White's book, there is a long discussion, a chapter, I think, related to dispersion. So maybe that will provide the answer.
Yes.
So, whatever pending questions we have for today's session, you may please email them. Right?
So, the pending one you already answered. So somebody's asking, is there any detector to detect the state of polarization?
Yeah, just now I just said
Yes.
it's the same thing, analyzing that thing. Just
Yes.
you have to just see, you have been told in the laboratory, suppose in an optical laboratory, you have been supplied a polarized light. Now you'll have to just figure out what light it is. So you just have to try this whole bag of tricks, put in a half quarter wave plate, put in a polarizer, rotate this, rotate that, and then come to your conclusion. So whatever feature matches, then you can check that. I mean, tally with that. Right?
There is just last request from a participant to summarize today's
Oh,
session.
yes. So today's discussion, we touched upon four broad topics. Today's discussion is, first was the superposition of two orthogonal linear waves. Orthogonal means perpendicular, one along the x and one along the y axis. And then, depending on the phase angle difference, we can get plane polarized state, elliptical and circular polarized states. And also we have analyzed the direction of the polarization depending on the phase angle sign. Plus sign will be anti-clockwise, minus sign will be clockwise. So that was the superposition of orthogonal states to give various states of polarization. That was the first broad topic. The second topic that we discussed today is retarder plates, full wave plate, quarter wave plate, half wave plate, all of these things. The third topic that we discussed today is the analysis of polarized light. Just now we discussed how do you detect how do you determine the nature of polarization in the case of a particular polarized light. So that is the third topic. And the fourth topic is optical activity. So basic history of optical activity and all of these things, and definitions, certain material behavior of optical activity, and then the mathematical theory of Fresnel, phenomenological theory, but it's quite an elegant theory, although it doesn't touch upon the physics of it in great detail. Fresnel did not know many things when he gave his theory about details. So basically four things: superposition of orthogonal waves, retarders, analysis of polarized light, and optical activity. 1, 2, 3, 4. So that is the summary.
All right. So thank you for today's session. And
Yes. Thank
we'll
you.
continue with the remaining sessions tomorrow,
Tomorrow at 2 p.m., I think.
2 p.m.
It's a 1 hour session. So we shall
It's a 1 hour session.
so we shall conclude all of these things with some little pending discussion. And meanwhile, you may kindly send me the questions that are pending from today's session. Right?
All right. Yeah.
Okay. Thank
Thank
you.
you.
Thank you, everyone.